Hi, I'm Scott Burleigh. I've been working on interplanetary networking for a long time. We're going to take a quick look at how delay-tolerant networking has gotten to where it is today, 27 years after we started off on it. Toward the end of 1997, the Consultative Committee for Space Data Systems was converging on a design for a file transfer protocol that would work across interplanetary distances. CFDP was a major step forward in standardizing flight mission communications, but it was limited to file transfer. CCSDS engineers saw in the internet a model for a more general and more powerful mission communications, an automated network spanning the solar system that would be able to overcome the challenges of transmitting data reliably over interplanetary distances. The first meeting to discuss interplanetary network was held at MCI Corporation in 1998 on February 2nd. The distinguished looking gentleman in the center is Vint Cerf, a co-inventor of the TCP/IP protocols that power the internet. That first meeting to discuss the general principles kicked off an intensive round of discussions of requirements, design, implementation, configuration, and so on that continue to this day. The first few months of conversations were informal. The first step toward formal organization of this work was registration of a domain name in September of the following year, IPNSIG.org, where IPNSIG stood for Interplanetary Networking Special Interest Group. Those early conversations grew to include networking experts from all over. The IPN core team presented their ideas to engineers at Caltech's Lee Center in October, and to the end-to-end research group of the Internet Research Task Force in December. Out of that research group discussion grew the decision to start a new research group for IPN itself. Early the next year, the new IPN research group presented design ideas to a meeting of next-generation Internet experts and drew the attention of the Defense Advanced Research Projects Agency, DARPA. DARPA was interested enough to begin an initial study of IPN concepts that might address some communication problems in defense. And by August of 2000, the team had converged on design to the point at which they could develop a first prototype of the bundle protocol that was to be the central technology of the IPN architecture, DTN 0. An internet draft description of that architecture was written in May of the following year and presented to the Internet Engineering Task Force, the authoritative body for standardization of internet technologies. Early in 2002, it was agreed that IPN ideas had the potential to be useful in many other environments besides interplanetary communications. So the IPN Research Group formally changed its name to the more general Delay-Tolerant Networking Research Group. In 2002 was also a year of using DTN 0 for intensive tabletop prototyping and testing, including an initial demonstration to deep space engineers at NASA's Jet Propulsion Laboratory. The core team used that experience to clarify the protocol details to the point at which they could be written down in a formal internet draft for the first time in 2003. And that formal specification then became the basis for a much more capable implementation of the bundle protocol named DTN1. DTN1 was to be used heavily as a research vehicle over the next year. Experience with the prototyping and the specification proved to be a solid enough foundation for an initial publication of the DTN architecture in a lengthy article in IEEE Communications magazine. Of course, the space program needs more than architecture and prototype code to operate flight missions. While the DTN core team continued formalizing the delay-tolerant networking protocols, the Jet Propulsion Laboratory was using the Mars Exploration Rover mission to prove the value of network communications in space. From the first days on the Martian surface in 2004, the MER rovers used the Mars Global Surveyor satellite to relay telemetry and images to the mission teams on Earth. DARPA's initial study of DTN determined that there really was something of value for the Defense Department in the architecture. Accordingly, In January of 2004, DARPA began a long-term program to develop disruption-tolerant networking technology. The program was to comprise 3 phases lasting 6 years altogether. Another key protocol in the IPN architecture is the liquid ladder transmission protocol, which serves roughly the same function in DTN as the TCP protocol does in the internet, assuring reliable delivery of data despite occasional packet loss. The first internet draft defining LTP was posted a little later in 2004. And at the end of 2004, a durable reference implementation of VP was completed. DTN2 will be used as the basis for DTN research for the next couple of decades. The team used 2005 and 2006 to hammer out the much more formal consensus specifications that IETF would require in order to publish requests for comments that would be retained as permanent reference documents. Meanwhile, a specifically spacecraft-oriented implementation of bundle protocol, as well as LTP and some other DTN protocols, was being developed and tested at NASA. The Interplanetary Overlay Network code base was first demonstrated at the IETF 67 meetings in November of 2006. Those RFCs began to be published in 2007. First, an informational RFC, RFC 4838, describing the DTN architecture. Then experimental RFC 5050, defining the bundle protocol. Also, phase 2 of the DARPA DTN program culminated in a successful demonstration at Fort AP Hill in November. The RFCs defining LTP were published in September of the following year. Even more exciting, from mid-October to mid-November of 2008, the operation of the DTN protocols on a spacecraft in deep space, about 15 million miles from Earth, was successfully demonstrated in a deep impact network experiment. At this point, the DTN implementation seemed stable enough to deploy to the International Space Station, ISS, on an experimental basis, forwarding data from science payloads called CBGAs. This trial operation phase began in June of 2009. At the beginning of 2010, the final phase of DARPA's DTN program culminated in extensive DTN exercises in Hawaii using a BP implementation developed by Raytheon BVN. Meanwhile, CCSDS was also beginning to see potential value in the DTN architecture. A CCSDS informative reference, 734.0-B-1, discussing rationale scenarios and requirements for DTN in space, was published in August. 2011 and 2012 and 2013 passed without notable events, while the IPN core team's energy turned itself to space station software support and protocol discussions in CCSDS and in the IETF. And then in January of 2014, Delay-Tolerant Networking was presented to the Speakers Conference at Google headquarters. And finally, later that year, those protocol discussions resulted in publication of another CCSDS informative reference, 730.1-G-1 on solar system internet architecture, and in the formation of a new DTN working group within IETF. At this point, the DTN RFCs published so far had all been informational and experimental RFCs. The new IETF DTN working group aimed to establish new standards track RFCs that internet operators could confidently use as the basis for commercial products. These RFCs would have to withstand even closer scrutiny than the earlier RFCs, so drafting and reviewing them would take longer. Meanwhile, though, in 2015, the CCSDS and DTN working group published 2 CCSDS standards that could similarly be used with confidence by space agencies. 734.1-B-1 for LTP and 734.2-B-1 for bundle protocol. In mid-2016, NASA decided that the experimental deployment of DTN on ISS had demonstrated the utility and stability of the technology, so operational use of DTN for communication with onboard science instruments began. Later that year, the Japan Aerospace Exploration Agency, which had been engaged in DTN research and development for 9 years, announced completion of a new implementation of DTN protocols for use on JAXA flight missions. In November of 2017, an imaginative DTN experiment further demonstrated the operational reach of DTN functionality. A photo taken at a base in Antarctica was delivered to an astronaut on ISS using DTN end-to-end via 2 TDRS contacts. Building on the confidence gained from operating DTN on ISS in low Earth orbit, in 2018, JPL began a project to build DTN into the Mission Operations Center software supporting the Deep Space Network. Accurate routing and forwarding procedures are critical to the operation of any network. In July of 2019, CCSDS published 734.3-B-1 standardizing schedule-aware bundle routing as prototyped in ION, the Interplanetary Overlay Network implementation of DTN. By 2020, the prospect of commercial use of DTN is beginning to attract some interest. In November of that year, researchers successfully demonstrated BP communication between nodes running in terrestrial cloud infrastructure. That's Amazon Web Service and Google Cloud. In February of 2021, the Interagency Operations Advisory Group, a consortium of the world's national space agencies, formally recommended the use of bundle protocol for future space missions. Later, in May, multiple demonstrations were conducted in which Earth-based DTN nodes instantiated using different BP implementations and operated by different agencies exchanged data with and through a CubeSat satellite named OPSSat in low Earth orbit. And in December, NASA launched the Lunar Communication Relay Demonstration Satellite, which was tasked with demonstrating bundle protocol communication between the Earth and the Moon over free space laser communication links. In January of 2022, the IETF DTN Working Group published the standards track RFCs they'd been working on for nearly 8 years. RFC 9171, bundle protocol, RFC 9172, bundle protocol security, RFC 9173, default security contexts, and RFC 9174, the TCP convergence layer adapter. Then in August, the Korean National Space Agency launched Danuri, the Korea Pathfinder Lunar Orbiter, KPLO. Danuri's onboard DTN implementation interoperates with the ION nodes that are now operational in the ground software of the Deep Space Network. In March of 2023, JAXA reported on the progress they were making in accelerating DTN protocol operation by running it in system-on-chip. And in November, NASA began a 6-month demonstration of communication via laser relay, the Illuma-T deployment to the International Space Station. High-rate data traffic over the bidirectional laser relay connections was conducted using HDTN, the high-rate DTN implementation developed at the Glenn Research Center. Then, in January of 2024, the Plankton Aerosol Cloud Ocean Ecosystem PACE Earth orbiting spacecraft was launched with a bundle protocol communication capability developed by Goddard Space Flight Center. To date, it has returned millions of bundles of science data with 0 data loss. The future of DTN, like the future of anything else, is not altogether certain. But DTN will be included in the architecture for the communications network supporting lunar missions through the rest of this decade. So there's reason to think that the DTN-powered solar system internet might just happen.